Right now, 1.5 million kilometers from Earth, the James Webb Space Telescope is looking at places no human eye could ever survive. It is not just taking pictures, it is reading ancient light, alien atmospheres, hidden chemistry, and the first structures after the Big Bang. And the problem is this: the deeper Webb looks, the more the universe refuses to match the story we wrote for it. Galaxies appear too early, black holes look too old, a distant planet carries a possible biological clue. The impossible thing Webb captured may not be one object. It may be reality itself. To understand why scientists are speaking so carefully, you have to understand what Webb is. It is not simply a stronger version of Hubble. Hubble orbits Earth, but Webb sits near the second Lagrange point, called L2, about 1.5 million kilometers away. Out there, the telescope, Earth, and Sun move together around our star, allowing Webb to keep its mirrors cold and its giant sun shield pointed toward heat. That sun shield is almost the size of a tennis court, built in 5 thin layers to block radiation from the Sun, Earth, and Moon. Behind it, Webb's golden mirror and infrared instruments operate in a silence colder than anything most machines could tolerate. Infrared light is the key. The oldest light in the universe has been stretched by cosmic expansion until it arrives as infrared radiation, invisible to our eyes, but readable to Webb. In simple words, Webb does not just see far away. It sees long ago. When Webb launched on December 25, 2021, scientists expected it to improve the cosmic story. They wanted sharper details about the first galaxies, the birth of stars, the atmospheres of distant planets, and hidden objects buried behind dust. But the hope was that the broad outline would remain familiar. The early universe should have been small, dim, messy, and slowly growing. Galaxies should have taken time to assemble. Black holes should have started small and grown by feeding. Chemistry should have followed a timeline. Then Webb opened its eyes. Almost immediately, astronomers began finding galaxies that looked too bright, too structured, and too mature for the universe's infancy. At first, some researchers warned that early candidates might be measurement errors, dust effects, or objects with wrongly estimated distances. That caution was necessary. Extraordinary claims need careful confirmation. But as spectroscopy improved, the pattern did not disappear. Some of the early objects remained real, and their distances were confirmed by the fingerprints of stretched light. One of the strongest examples is MOEMZ 14, a remarkably luminous galaxy confirmed at a redshift around 14. 4, meaning Webb sees it as it was only about 280 million years after the Big Bang. On a human scale, 280 million years sounds enormous. On the cosmic scale, it is almost childhood. The universe is about 8 billion years old. Seeing a bright galaxy this early is like walking into a nursery and finding something already building a city. MOEMZ 14 is not important only because it is distant. It is important because it is bright, compact, and already chemically interesting. The research team reported evidence of emission features and nitrogen enrichment, suggesting that star formation and chemical processing had already moved faster than many models expected. This does not mean physics is broken. It means the recipe for early galaxy formation may have missing ingredients. Stars may have formed more efficiently. Dense clusters may have evolved differently. The first generations may have altered their surroundings faster than predicted. The most disturbing part is that MOEMZ 14 is not alone. Webb has revealed a population of surprisingly bright early galaxies. Some analyses suggest there are far more of these luminous objects than pre-Webb models expected. That gap matters. One unusual galaxy can be explained. A growing population becomes a warning. If the map says the road should be empty, but Webb keeps finding traffic, the map needs revision. That is why astronomers are not panicking, but they are paying attention. The early universe is becoming less like a slow dawn and more like an explosion of structure. Something allowed the first galaxies to ignite, organize, and enrich themselves quickly. The standard cosmological model may still survive, but the detailed physics of galaxy formation may need serious surgery. Webb is not destroying science. It is doing what great instruments do, forcing science to become more honest. Then came the black holes. In the modern universe, supermassive black holes sit in the centers of large galaxies. They can contain millions or billions of times the mass of the Sun. The usual story says they begin as smaller seeds, perhaps from dead massive stars, and then grow by swallowing gas and merging with other black holes. That takes time. So in the very early universe, astronomers expected to find young, growing black holes, not monsters that already seemed mature. Webb found the monsters. One of the biggest mysteries is the class of objects known as little red dots. The name sounds almost harmless, but the objects are not. They are compact, extremely distant, and surprisingly red sources that appeared in Webb data from the early universe. For a while, researchers debated what they were. Were they dense star clusters, dusty galaxies, hidden active galactic nuclei, or something stranger? The answer may not be the same for every object, but one possibility keeps growing stronger. Many little red dots may hide rapidly feeding black holes. A major example is Canucks LRD Z8. 6. An early little red dot linked with an actively growing supermassive black hole when the universe was only hundreds of millions of years old. This is not just another distant object. It is a clue that black hole growth began extremely early, possibly before host galaxies had time to settle into familiar shapes. The monster may not have waited for the house. In some cases, the house may have formed around the monster. The idea becomes even more dramatic with possible direct collapse black holes. In the ordinary picture, black holes are born from stars. A massive star dies, collapses, and leaves behind a black hole seed. But direct collapse suggests a shortcut. Under extreme early universe conditions, huge clouds of gas could collapse directly into massive black hole seeds, skipping the star stage. For years, this was theory. Webb has now found candidates that make that theory feel less like speculation and more like a necessary solution. One NASA-highlighted case involves the so-called infinity galaxy, where Webb observations support the possibility of a direct collapse black hole. If that interpretation holds, it would help explain why the young universe contains black holes that seem too massive too soon. Nature may have had more than one way to build a cosmic monster. Some black holes may have been born heavy. This changes the emotional weight of Webb's discoveries. We are not just learning that galaxies formed earlier, we are learning that the engines inside them may have ignited earlier, too. Black holes may have shaped the growth of galaxies from the beginning, heating gas, driving winds, regulating star formation, and leaving fingerprints on the cosmic web before the universe was even 1 billion years old. Webb is turning black holes from late-stage giants into possible architects of cosmic dawn. And while one part of Webb was looking back toward the first galaxies, another was looking at a world 124 light-years away. The planet is K2-18b. It orbits a red dwarf star in the habitable zone where conditions could allow liquid water under the right circumstances. K2-18b is not Earth. It is larger, more massive, and likely belongs to a class of planets between rocky worlds and gas giants. Some scientists describe it as a possible Hycean world, a planet with a hydrogen-rich atmosphere and a global ocean beneath. That idea is still debated, but it makes K2-18b one of the most watched exoplanets in astronomy. Webb studies worlds like this through transmission spectroscopy. When a planet passes in front of its star, some starlight filters through the planet's atmosphere. Molecules absorb specific wavelengths, leaving fingerprints in the light. From those fingerprints, scientists can infer gases like carbon dioxide, methane, water vapor, or other compounds. It is one of the most difficult measurements in astronomy because the signal is tiny, but Webb was built for exactly this kind of work. In 2025, researchers reported possible signatures of dimethyl sulfide and dimethyl disulfide in the atmosphere of K2-18b. On Earth, dimethyl sulfide is produced largely by marine life, especially microscopic organisms in the oceans. That makes the molecule exciting. But the honest version matters. This is not proof of life. The confidence level was around 3 sigma, below the 5 sigma standard scientists usually want for major claims. Other researchers have questioned whether the signal could be explained by alternative chemistry, data processing choices, or different atmospheric models. And yet, even with every caution included, the result is historic. For the first time, we are no longer only imagining how to search for life's chemical fingerprints on distant worlds. We are actually doing it. Webb has moved the question from philosophy into measurement. The K2-18b signal may vanish with more data, or it may strengthen. Either outcome will teach us something. But if it survives future observations, the world changes. That is why the Webb story is not only about ancient galaxies, it is about 2 frontiers at once, the beginning of the universe and the possibility of life beyond Earth. One frontier asks how matter became galaxies, stars, planets, and black holes. The other asks whether those planets can become living worlds. Webb is standing between both questions, reading infrared light from the first cosmic dawn and from alien skies in the same mission. Then, in 2025, something from another star system entered our own neighborhood. The object was 3I Atlas, the third confirmed interstellar object observed passing through the solar system. The first was Oumuamua in 2017. The second was Borisov in 2019. 3I Atlas was different because Webb was ready. NASA's observation timeline shows Webb targeted the comet with its near-infrared spectrograph in August 2025, allowing scientists to study material that did not form around our sun. Think about what that means. Usually, studying another planetary system requires reading light across unimaginable distance. But an interstellar object is physical material delivered to our doorstep. It is a sample from somewhere else, not in a laboratory, but close enough for telescopes to analyze. Webb's data showed a chemically unusual coma with strong carbon dioxide and other volatiles. Later, work explored carbon monoxide, water, methane, methanol, and the structure of the coma after the comet passed near the Sun. This matters because interstellar objects are messengers from planetary systems we may never visit. Their chemistry records the environment where they formed, the radiation they endured, and the processes that shaped them before they were ejected into galactic space. If 3 interstellar objects have been discovered in less than a decade, then such visitors may be common. The solar system may be crossed constantly by fragments from other stars, and only now are we learning to catch them. Webb also keeps surprising scientists closer to home. In August 2025, researchers using Webb's NIRCam discovered a previously unknown tiny moon orbiting Uranus. The moon, temporarily designated S2025U1, is estimated to be only about 10 kilometers wide. It was missed by earlier telescopes and even by Voyager 2 during its 1986 Uranus flyby. That is not because earlier missions were careless. It is because the moon is extremely faint, small, and difficult to see. Webb revealed that even in our own solar system, the inventory is not complete. Uranus has also become a target for Webb's atmospheric power. With NIRSpec, scientists mapped the planet's upper atmosphere and auroras in new detail, confirming that the upper atmosphere has continued cooling over decades. Uranus is not just a blue-green disk. It is a strange, tilted ice giant with an offset magnetic field, complex auroras, and a weather system that still challenges planetary models. Webb's infrared sensitivity turns it from a distant planet into a laboratory for understanding ice giants and similar exoplanets. Then came one of the strangest nearby findings, an unidentified absorption feature on Titan and Pluto. In 2026, researchers reported a feature around 11 micrometers in Webb spectra of both worlds. Titan has a thick nitrogen-methane atmosphere and hydrocarbon chemistry. Pluto has a thin atmosphere and a frozen surface. They are very different places, yet both showed a mysterious spectral signature that does not clearly match known laboratory spectra. It may be a known compound in an untested form or mixture. It may reveal chemistry not yet fully characterized. That discovery is important because it proves Webb is not only rewriting the distant universe, it is also reopening old cases in our own solar system. Pluto and Titan have been studied for decades. Titan was visited by Cassini and Huygens. Pluto was visited by New Horizons. Yet Webb found a clue no previous mission had resolved. The lesson is simple. Sometimes the unknown is not far away. Sometimes it is hiding in light we were never able to read properly. Webb has even changed how astronomers study exploding stars. In 2026, ESA highlighted a case where Webb helped identify a supernova progenitor star that had been hidden by dust, invisible to Hubble. Infrared light can pierce dusty regions that visible light cannot. This matters because scientists have long wondered why certain expected red supergiant progenitors seemed missing before supernova explosions. Webb suggests at least some were not missing at all. They were buried behind their own dust, waiting for an infrared telescope to reveal them. This is the pattern. Webb does not merely make prettier pictures. It removes excuses. If dust blocked the view, Webb looks through dust. If early galaxies were too faint, Webb reaches deeper. If exoplanet atmospheres were too subtle, Webb measures them more carefully. If small moons were too dim, Webb sees them. Again and again, the telescope exposes what older instruments could not. And the pace has not slowed. In July 2026, Webb marked its 4th science anniversary with new images of Centaurus A, a nearby galaxy shaped by a past merger and powered by an active supermassive black hole. Webb's infrared view revealed dust lanes, star-forming regions, ionized gas, and hidden structure around the galaxy's core. Even a familiar object became unfamiliar when seen with better eyes. Around the same time, researchers announced that Webb had helped capture at least 6 galaxies merging in the early universe into a system that may grow into one of the largest galaxies in a cluster. This is not a quiet scene. It is cosmic construction by collision, with galaxies falling together, gas compressing, stars igniting, and a central black hole feeding. Observations like this show how the universe builds giants, not as smooth sculptures, but through violence. So when the title says, Webb captured something impossible, the safest truth is this: Webb has captured many things that were impossible for our older models to comfortably explain. Not impossible in the sense that they violate reality, but impossible in the sense that they violate expectation. Science does not collapse when this happens. Science begins. The early galaxies tell us star formation may have accelerated faster than expected. The little red dots tell us black holes may have grown behind thick curtains of gas and dust. The direct collapse candidates tell us heavy black hole seeds may have formed without waiting for stars to die. K2-18b tells us biosignature searches are now real, even if not yet conclusive. 3i Atlas tells us other solar systems may be sending frozen fragments through our neighborhood. Titan and Pluto tell us our own worlds still hide unidentified chemistry. This is not one discovery, it is a pattern of surprises. The reason this feels so different from earlier astronomy is that Webb combines sensitivity with spectroscopy. A picture can show that something exists, but a spectrum explains what it is made of, how fast it is moving, how hot it may be, and sometimes how it formed. That is why the telescope keeps turning headlines into harder questions. A bright dot becomes a galaxy with a distance. A red smudge becomes a hidden black hole candidate. A dip in starlight becomes a molecule in an atmosphere. Webb is not only expanding the catalog of objects, it is exposing their physics. That also explains why honest scientists avoid simple viral claims. When Webb sees an early galaxy, researchers must confirm its redshift. When it sees a possible biosignature, teams must test whether another molecule or cloud model could imitate the same signal. When it sees a black hole candidate, astronomers compare stars, dust, gas, and active galactic nucleus models before calling it a monster. This caution is not weakness. It is the reason the discoveries matter. The strongest Webb results are powerful precisely because they survive attempts to explain them away. The public often hears the phrase impossible and thinks scientists have no answer. The better meaning is sharper. Impossible means our first explanation is insufficient. It means the universe has handed us data that does not fit neatly into the simplest version of the story. Maybe the first stars formed in unusually dense clusters. Maybe early gas cooled and collapsed more efficiently. Maybe black hole seeds were born heavier than we assumed. Maybe sub-Neptune planets can produce exotic sulfur chemistry without life. Every possibility is being tested, but none of them make Webb less exciting. They make it more dangerous to old assumptions. And Webb's advantage is not ending soon. Its launch was so precise that it saved fuel needed for station keeping around L2, extending the mission potential beyond the minimum design lifetime. Its instruments continue to perform at a level that allows astronomers to ask questions no previous observatory could touch. That means today's impossible discoveries are not the final list. They are the first wave. More early galaxies will be measured. More little red dots will be tested. More exoplanets will pass in front of their stars. More solar system worlds will be scanned for hidden chemistry. The telescope is still building the evidence. That is what makes the moment feel historic instead of merely interesting. We are not watching one dramatic announcement. We are watching a new observing era unfold in real time, where every month adds pressure to old models and detail to new ones. The universe has not changed. Our ability to catch it in the act has changed. And because Webb reads infrared light, even the coldest, dustiest, oldest regions can now speak in wavelengths earlier telescopes mostly missed completely and misunderstood before. The future will decide which surprises become revolutions. NASA's Nancy Grace Roman Space Telescope is expected to survey huge areas of sky, turning Webb's rare early galaxy discoveries into large statistical samples. Future missions like the Habitable Worlds Observatory are being planned to search more directly for signs of life on Earth-like planets. Webb is raising questions that the next generation of telescopes will be built to answer. But that does not make this moment smaller. It makes it bigger. We are living through the first years of a telescope that can look back toward cosmic dawn and sideways toward alien atmospheres. It is still early in its mission, and already it has found galaxies too bright, black holes too early, chemistry too strange, and possible biosignatures too important to ignore. Somewhere in the data Webb has already collected. The next shock may be waiting for human eyes. The universe did not promise to match our theories. Our models are maps, not commandments. Webb is now walking through the territory and showing us where the map bends, breaks, or leaves out entire continents. That is why astronomers are careful, excited, and uneasy at the same time. The telescope is not telling us that everything we know is wrong. It is telling us that everything we know is incomplete. And maybe that is the most powerful discovery of all. A machine at L2, hidden behind a sunshield, freezing in darkness, is showing humanity that the universe is more creative than our equations. It built galaxies quickly. It may have built black holes first. It hides chemistry on frozen worlds. It sends interstellar comets through our system. And on at least one distant planet, it has left a chemical clue that may be nothing, or maybe the beginning of the biggest story ever told. Webb is still watching. Every image, every spectrum, every faint infrared signal is a piece of a story older than Earth and larger than imagination. The impossible thing it captured is not a single object. It is the realization that the universe still has chapters we have never read, and the next one may already be crossing space, quietly toward the telescope right now.